All right, so what we're going over today, and Grayson, can I get you to turn the front bank of lights off for me? Thanks. Okay, what we're going over today are the different types of measured values that we might deal with in Science 10. Okay, at least in the physics part of it. All right, so what we're looking at are quantities that have just a magnitude or a size, and some that have a size as well as a direction. All right. For example, how many of you right now would say that speed and velocity are the same thing? Speed and velocity are the same thing, right? I mean, that's what most of us would say, right? Because we use those terms interchangeably in the English language. And while they do both measure similar things, they measure essentially how fast you're going, one of them doesn't just measure how fast you're going, it also measures how fast you're going in a particular direction. All right, so while they both measure, okay, how quickly you're covering distance, one of them is also concerned with what way you're going while you do that. Okay, any type of measured quantity that deals with direction as well as size is called a vector quantity. Okay, anything that just has a size is a scalar quantity. So, for example, okay, if I say to somebody, my mass is 75 kilograms, I've just given them a scalar quantity. Because I don't say I'm 75 kilograms north, because that doesn't make any sense. Okay, my mass is how much of me there is. Some days I wish there was less of it, but okay, that's how much of me there is. It doesn't have a direction. That's just how much of me there is. It's not a vector quantity. It's a scalar quantity. Okay, in the same way, if I said, it takes 4 days for mold to start growing on bread. Okay, does time have a vector? What do you think? I didn't say it took 4 days south. I said it took 4 days for mold to grow. Okay, I don't give a direction on time either. As far as I know, time only goes one way, forward. If you have a time machine at home that can make it go the other way, you and I need to talk. Okay, there's a few things in my life I would change. All right, so time, as far as I know, only goes one way. It's also a scalar quantity. Okay, so the big things here, we need to understand there's many ways of measuring how far apart or how fast objects are going. We need to differentiate between distance and displacement, okay, as well as speed and velocity. Now, we already talked about speed. Speed is a scalar quantity. Okay, velocity is a vector quantity. That's why if you get pulled over on the Deerfoot for going 140 kilometers an hour, you get a speeding ticket. You never get a velocitying ticket. Okay? The police generally only care about how fast you're going, unless, of course, you are going really, really fast and the wrong way. Then you would probably get 2 separate tickets. Okay? Everyone follow me there? Okay, for distance and displacement, similar relationship. Distance is a scalar quantity. If I tell someone how far apart 2 places are, that's the distance. But if I tell them how far apart and in what direction, then I'm telling them the displacement. Okay, so displacement will also have a direction on it. So as a result, it is a vector quantity. Okay, and then we'll be solving problems related to motion using these 2 formulas. You're probably looking at those formulas and saying Coder's going senile. Those are the same formulas. They're not. Okay? This V has an arrow over top of it. Thus, it stands for something different. Okay? This V with the arrow over top stands for velocity, whereas this V stands for speed. All right? Scalar quantities don't get little arrows over top because they don't have direction. Everyone follow? All right. Now, what we have to understand here as well is that the way we communicate things to each other in our society, in North American society especially, is really, really physically wrong. All right? I'll give you an example here. Okay? If I ask Kennedy here how far it is to Edmonton, how far is it to Edmonton? Sure. Yeah, 4 hours, 3 hours. Okay, and she even asked me time-wise. She was thinking I might have wanted a different answer, which I actually did, but she gave me the answer most people give. How many of you were thinking 3 or 4 hours in your head when I asked how far it was to Edmonton? Because that's how we in North America think about distance. Okay? Did she give me a distance? She gave me what? Time. And that's exactly what we were all thinking. It takes 3 hours to get there. Why do we think that? Because we have a vast interconnected system of roads. Okay? And usually when we go from one place to another, we get in our car and we follow the road there. The road has a speed limit, so we know about how long it will take. Okay? If you went to Europe and you asked somebody how far apart are these two cities, they would tell you how far apart they are in kilometers. Okay? Because they usually travel in different ways. Right? They just think about things a little differently than we do. Right? It just has to do, it's a cultural thing. We always seem to give distances in time when we shouldn't. Okay? So we kind of have to change the way we think a little bit. All right? The real answer there should have been that it's about 300 kilometers. Okay? Everyone with me there? All right. So, if we've ever gone hiking off trail or done any orienteering, okay, you know that the way we describe travel in everyday life is effective at only getting you hopelessly lost. I'll give you an example. My friend and I were hiking in Kootenay National Park, and we'd been hiking all day. It was our longest day. It was a 30-kilometer day, and we had to go up and down through 2 passes. So we were pretty tired, and we're thinking, man, the campground we're supposed to get to it can't be very far. We've been walking forever. It can't be far away. It can't be far away. This guy comes the other direction, comes trotting up this hill, making pretty good time. Okay, comes up past us, and we're like, hey, you must have come from the campground. How far is it? He's like, oh, it's 20 minutes. We're like, oh, sweet, it's only 20 minutes from here. Okay, we didn't think about a couple of things. First off, this guy looked like he could have been a Navy SEAL. Okay, he was carrying like a pack that was as big as ours, but he was running, and he was running uphill with it on. Okay, so we weren't. We were struggling along. Right? And he told us it was 20 minutes. So we walk along this trail, and it was like at 45 minutes to an hour before we finally got to the campground, and we were cursing this guy. Okay, like we're gonna go drop off our packs and run after that guy. We didn't ever caught him, but anyways, and we're gonna go get that guy because he totally lied to us about how far it was. And we're just bagged and tired. Okay, but again, he told us how long it took him to get from the campground to where we were. What was different between him and us? Yeah, he was running. He was in better shape than us. He was fresh because he just started. We'd been walking all day. Okay, he probably could have run 2 marathons back to back and not gotten a sweat broken. Like he was just. His velocity was different. His speed was different than ours. Okay, the distance traveled was the same, but because he was so much faster than us, his time was different. And that's why you can't give distances as a time. Sure, most days it probably takes 3 hours to get to Edmonton from here. But are there days where it takes longer than that? Yeah, there's days where it can take a lot longer than that. That's under ideal conditions where you can drive the speed limit the whole way. All right? So when someone asks for how far is something, you need to give them the right measurements. Okay? So it's important when you read a question in this class. If it says how far away is something, don't give me a time. Okay? Give me something in meters or kilometers. All right. Now, let's say I'm right here at this campground. Okay? This campground is Seldom Inn Campground is what it's called. And I want to go over to this campground here, which is Snake Indian Falls Campground. Just outside of that campground is a sign. And that sign says that it's 27 kilometers to that campground. Is that a scalar quantity or a vector quantity? It's scalar. It just tells me it's 27 kilometers. What is that sign assuming I'm going to do? Follow the path, which would be a good assumption because that's the smartest way to get there. All right? If that sign said it was, let's say, 19 kilometers at 35 degrees north of east, then it would be saying, go this way. Would that be the smartest way to get there? No. All right? I mean, look at all the rivers, and there's this glacier here, and there'd be problems with doing that. Right? So there are situations where a scalar quantity is warranted. Right? If there's a definite path from one place to another, that makes sense. All of the signs that we have on the road are all given scalar quantities, assuming we will follow the roads. Okay? What if you're an airplane pilot? Do you want a scalar description of how far it is from, let's say, Calgary to Florida? You probably don't, right? Because there's not a road you're going to follow in your plane at 30,000 feet. Okay, you can't even see the roads from that high up. So you need a vector description. What angle or what direction do I need to head the plane in? And then how far do I need to go in that direction? You need a vector description. Okay, if you're sailing on the ocean, same thing. There's no roads to follow. You need vector descriptions. How far and in what direction do I need to go? All right. So they both have their uses. Right. We often get the idea that scalar quantities are less accurate or less useful. Okay. They're not. They're just as accurate. They're just as useful in the right situations. Okay. Does that make sense? Oh, you're saying yes? Okay. All right. So if we say Calgary's 40 kilometers away, we're giving a scalar description of where Calgary is. What are we going to assume? We're going to assume people are going to get on the road and follow it to Calgary. Okay, safe assumption. If I tell them Calgary is, let's say I give them an angle, okay, or a direction and a distance, then I could assume they have a helicopter and they could actually fly along that straight line from here to Calgary. All right, or maybe they would walk, which would be difficult because you have to cross the river, but okay, stuff like that. If you're doing that on foot, obviously that's a little different. Okay, so 40 kilometers away is a scalar description. Okay, scalar descriptions, okay, we've only said how far, not which direction. All right, now this should not say more accurate. This should say more descriptive. Did I change that in your notes? Just check your notes. I thought I changed it to descriptive in your notes, but I may not have. Okay. A more descriptive description of where Calgary is would be that Calgary is 40 kilometers away on a vector of 13 degrees east of north. All right, so here's Okotoks, okay, and well, it should be west of north according to this graph, this map, but okay. So there's straight north, and then this would be the angle to get to Calgary. It's a few degrees west of north, okay, in order to do that. Everyone follow me there? Okay, so that's a vector description. Okay, a vector description not only tells us where Calgary is, but also how to get there. Okay, so it gives us a magnitude and direction. In Science 10, we're not going to deal with compass directions because it brings trigonometry in. All right, you guys will only deal with what we call one-dimensional vectors. Forward and backward, north and south, okay, right and left, up and down. I'm running out of examples, but you get the idea. Okay, everything you deal with will be, the other direction will be the exact opposite, so you'll always have positive and negative values. All right, so if we give the distance an object travels, distance is scalar. All right. So let's say it's 4 kilometers from my house to Walmart. That's a scalar description of how far it is from my house to Walmart. Okay. However, the displacement for the same trip is different. Why is it different? Well, I have the map here. No, I don't. Okay. So let's assume that when I'm going from my house to Sprawlmart, okay, let's say that my house is here, and let's say that this here's the river. Okay. And here's Wally World over here. Can I, on foot, go in a straight line from my house to Walmart? Really? Aren't there going to be buildings and things like that in my way? I would think there probably are. Buildings, trees, any number of things I can't just pass through. Okay? So I can't go in a straight line from my house to Walmart. I can just do this. I can, come out of my house and then go down the road and make some turns and follow over the bridge and then, follow Southridge Drive and then end up at Walmart. All right? That would be 4 kilometers. Everybody with me? That's the distance I would have to travel to get to Walmart from my house. But if I was fortunate enough to have a helicopter, I would not shop at Walmart because I'd be filthy rich. Okay? But I don't have a helicopter, so I can't unfortunately do this. Okay? That line represents my displacement from my house when I go to Walmart. I didn't actually go that way, but displacement always measures how far and in what direction in a straight line from your starting point to your ending point you've traveled. So it's always going to be shorter than distance, unless you actually were able to travel in a straight line, and then they'd be equal. Okay, but almost always your displacement will be a smaller distance. Now, I also have to give a direction on that. Okay, now I haven't drawn it the same way that the picture shows. Okay, but I would say 38 degrees north of west, which according to this it isn't. But all right, everyone follow me there? I would have a magnitude. This line is 2.8 kilometers long, okay, and a direction. Let's just say in this case here, let's reverse it. Then it'll be north of west. Here's Walmart. Here's my house. We'll just reverse it. Okay? What's that? I didn't draw where I actually lived. It's not my first day. Okay, so here's straight west, right? And so this angle here would be 38 degrees north of west. All right? Everybody got me on that one? And if you could pinpoint where I live from this crappy diagram, you're pretty good. Okay. All right, so the big thing to remember here, guys, okay, displacement then, okay, is our straight line distance. So displacement and distance are measures of the same thing, but they look at it from different points of view. All right, so let's say that it takes me a half an hour to walk to Walmart. So now I know that my distance traveled is 4 kilometers. The time it took me is a half an hour. How fast did I walk? What was my speed? Okay, well here's the formula. Speed equals distance over time. Okay, and I have distance and time here, 4.5 an hour. All right, so if I go 4 kilometers divided by a half an hour, I should get 8 kilometers per hour. Agreed? Right? If I walked 4 kilometers in half an hour, I'd walk 8 kilometers in an hour. Okay, so my speed's 8 kilometers per hour. Now, what's my velocity? No, my velocity is displacement over time. So what was my displacement here? Dom? Right, my displacement was 2.8 kilometers, 38 degrees north of west. Okay, so I'd have 2.8 kilometers at 38 degrees north of west. Okay, and that still took me a half an hour. Right, so my velocity then ends up being 5.6 kilometers per hour at 38 degrees north of west. Why do I have to include that? Tom? Right. Velocity is a vector quantity, so I have to leave the direction on. Does it make sense that my displacement and my velocity should be in the same direction? Okay, think about this. If you drive north, is it possible, let's say you drive 100 kilometers per hour north for 2 hours, is it possible for you to end up east of where you started by doing that? Okay, that's why they should always have the same direction. All right, your displacement and your velocity should always have the same direction. Everyone follow me there? Okay. Now, thinking about the idea here, distance is how far you go. Doesn't matter about what direction you go. Distance is just how far you go. Okay? Displacement is how far you go and in what direction from your starting position. So now, I walk exactly the same route all the way back. Okay, so I got whatever I wanted at Walmart, okay, and now I follow the same route all the way back to my house. What's my total distance traveled? Right, times by 2, 8 kilometers. Okay, it was 4 kilometers to Walmart, it's 4 kilometers back to my house. Followed the same route. Okay, my total distance traveled is 8 kilometers. What's my total displacement? Nope. Remember, displacement is how far and in what direction from where I started I end up. I started at my house. I ended up at my house. What's my displacement? Nope. It's 0. I ended up back where I started. I might have traveled 8 kilometers in doing that, Okay, my distance was 8 kilometers, but because I ended up back where I started, my final position and my initial position are the same place. I technically didn't go anywhere. Okay, you guys follow me there? That's the difference between a vector quantity and a scalar quantity. When direction is involved, if you end up back where you started, you could have no displacement whatsoever. Okay? Everybody all right with that? That sort of makes sense? That's something to keep in mind. Okay, we run into questions like that fairly often. Jack, question? Oh, okay. All right, so speed and velocity have a similar relationship. All right, so let's say that I did this whole trip where I walked there and back. Took me a half an hour to walk back as well. Is my speed still 8 kilometers per hour? Yeah, because I went 4 kilometers there in a half an hour, 4 kilometers back in a half an hour. My speed is 8 kilometers per hour because my total distance is 8, and my total time is 1 hour, 8 kilometers per hour. What's my velocity, though, for the whole trip? Okay, think about this. Velocity is displacement over time. And we just said displacement, if I go there and back, is what? Is 0. Well, what's 0 divided by anything? 0. All right, then my velocity is also 0. Okay? This is why the instrumentation in your car only deals with scalar quantities. Okay? The odometer in your car, the thing that measures how far you've gone, that measures distance. It would be utterly useless for it to measure displacement, because every time you came home, it would read the same number, however far it is from the car dealership to your house. Okay? Every day you come back, it would say that your car has like 4 kilometers on it, because you would keep returning to the same spot. It's useless for it to do that. Okay? In the same way, it can't measure your velocity with its speedo either. That's why it's called a speedometer and not a velocityometer. Okay? It measures how fast you're going, not which direction you're going. All right. So this here, guys, this paragraph is just dealing with that calculation that we did just a minute ago for the trip to Walmart. Okay? The second part here is dealing with what we talked about after that. What happens when I come all the way back? Okay. All right. So we're going to try a couple of sample problems here that you might encounter in this class here. All right. So I have this bus, and it travels 100 kilometers north in 1.2 hours. And then it turns and travels 62 kilometers south in 0.9 hours. I want to find the average velocity of the bus. Okay, so write this one down. Okay, write this one down as an example in your notes here. And I want you to try it before I do it. So how many people are doing an average as they've been taught to do an average their whole life? They're taking those two numbers, adding them together, and dividing by 2. Okay? It's okay to say that because that's how you've been taught to do it. It unfortunately doesn't work here, does it? Okay? It doesn't work here, okay, for this reason. Okay? There's a couple reasons why that doesn't work in this situation. First off, those two velocities are in different directions. Okay? The second reason it doesn't work is because they don't represent equal parts of the trip either. Okay? When we do an average of things, usually each one of the things you're adding together represents an equal part of the whole. For example, if I was to calculate the class average on a quiz in this class, I take each one of your scores, add them together, and divide by the number of people in the class, because each one of you represents an equal part of the class, so I can treat you that way. Okay? But in this case, one of the parts of this trip is considerably longer than the other, and as a result, has more of an effect on the average than the other does. Okay? So, anytime you're asked to find the average velocity, okay, you have the total displacement over the total time. Okay? Everybody with me there? So this thing goes 100 kilometers north, and then it goes 62 kilometers south. How far from where it started does it end up? Not 28. 38. Yeah, okay? Ends up 38 kilometers from where it started, right? I go 100 minus 62, and that's how far from the starting position I end up. So 38 kilometers, and that is north, okay? Because I'm looking for displacement here. So 38 kilometers north is how far is my displacement, how far and in what direction I am. How long does this whole thing take? Well, it looks to me like it takes 2.1 hours. Agreed? Okay. All right, how did I get that? I added 1.2 and 0.9. So now I have the total displacement divided by the total time. That will give me 18.1 kilometers per hour. All right, and what should also be on here? 18 kilometers per hour north. If my displacement is north, my velocity is north. Okay? So not too often are you going to get a question that's just, here's a distance and here's a time, calculate velocity. That's, I think, beneath you guys. Okay? I think you guys are smarter than that. Okay? We can work on tougher problems than that. All right? This simply puts in a couple of extra pieces. All right? Okay, so we'll do a couple examples here, guys. Let's try this one. This is a basic one. Really, really basic. Okay, how far does a jogger run in 1.5 hours if his average speed is 2.2 meters per second? Now, anyone see a problem with the numbers you're given in this question? Well, meters per second is a unit for time. In fact, or sorry, is a unit for speed. It's the one we use actually most often. But what's wrong with the other units we were given? What? Right. Hours and seconds both measure time, but they're not the same units. So I can't divide them. It's like dividing apples and oranges. Okay? I don't know what I get then. An apple orange or something, but it doesn't work. Okay? So I need to make sure that my units all match. Okay? If I've got meters per second here, I should make sure that my time is also in seconds. How do I convert hours to seconds? Yeah, or divide by 3600. Yes. Okay? Actually, sorry, not divide. I would need a bigger number. There'd be more seconds than hours. So I wouldn't divide, I would multiply. Okay? There are 3600 seconds in an hour. All right? So 1.5 times 3600 should give me my amount of time in seconds. All right? So 1.5 times 3600 will give me my time in seconds. All right, so 5,400 seconds. All right, so now I have time, and the 2.2 was a speed. How do I know it was a speed and not a velocity? Zach? Yeah, it says average speed. It also has no what? It has no direction on it. All right. It asks me to find out how far. If it says how far, that's distance. All right? If it's looking for displacement, it'll either say how far and in what direction, or it'll simply say what is the displacement. All right? So it's important to know how a question might ask for one thing or the other. All right, I'm looking for D. So V equals D over T. To manipulate this formula, we will not use a triangle under penalty of death. Okay? No triangles can be used here. All right? If I want to get D by itself, how do I move T over to here? I just do it. Yeah, I could. Okay? But what do I mathematically do? Right. Multiply both sides by T, right? When you want to move something, you do the opposite. And whatever you do to one side, you do to the other. Those are the only two rules you need to know about algebra. Okay? I teach science and physics, and those are the only two rules I know about algebra. So it must be good enough. Okay? If we remember those two rules, we don't need triangles, which will fail us on the next formula I teach you anyway, okay? Because it's got more than 3 variables. All right, so T times V equals D. All right, so we'll take our time, 5,400, and multiply by 2.22. And that'll tell us how far we're going to go. And it should come out to 11,988 meters. All right. Everybody okay with that? Manipulating's not too tough, right? Okay. All right, what I'm going to do is I've got a worksheet here that's got just some practice stuff on it like this. In fact, this is the first question from the worksheet. All right, so you're just going to be using V equals D over T, okay, practicing manipulating, all right, stuff like that. The first side of the sheet is the one I want you working on today. There's no direction on the first side. Okay, you don't have to worry about any vector quantities or positives and negatives. We'll talk about those tomorrow. All right. Okay, so for number 3, the key here is that you're actually dealing with each run separately. All right, so for the first part here, you're taking your distance and your time. All right, how fast does it go when it's making the run to the right? Okay, and then how fast does it go when it's making the run to the left? So when you're going to the left, it's just 604 meters, but now it's in 2.22 seconds. So it's 2 separate calculations. Does that make sense? No. Okay, so number 4 is a 2-part question. We've got the first part of the question where it travels 11 kilometers at 21 meters per second. Then the second part, it goes 1 kilometer at 4.2 meters per second. It wants us to find the average velocity for the whole trip. Now here's what we have to remember. Average velocity, I need the total distance, or sorry, it should say speed, but we'll say total distance over total time. Okay, so I need the totals here. Do I have any of the times? No, I don't. All right. Can I find the time for each part? So in part 1, I've got the distance traveled is 11,000 meters. Right? I have to turn it into meters because my speed was given in meters per second. Okay? And my speed was 21 meters per second. With D and V, can I find T? Can I do that for both parts then? If I know the time for each part, then I know the time for the whole trip by adding them together. Everyone follow? Okay, and that's essentially the way you do any question like this that has 2 parts. All right, you just split it up into the parts and write down what you know for each part. Okay, I know in part 2 it's 1,000 meters and the speed is 4.2 meters per second. So I can find the time for each one. So for the first one here, I have to go V equals D over T, and I've got to manipulate for T. So I multiply both sides by T so that it's on top, and then I divide both sides by V. So T equals D over V. So that's going to mean for this one, 11,000 over 21. Okay, so, well, not times, 11. Okay, gives me 523.81 seconds, we'll say. Alright, so that's how long the first part takes. I do the same thing here. T equals D over V, 1,000 divided by 4.2. Alright, that part takes 238.1 seconds. Everybody with me so far? Okay, all I've done is 2 separate V equals D over T calculations. Now, I'm going to go back to this, the total over the total. Well, if it goes 11,000 and then 1,000, and they're in the same direction, how far did it go in total? 12,000. My total displacement is 12,000 meters. Okay, because it never said they were in opposite directions, so I have to assume they're both forward. Okay, 12,000 meters, and then I add the 2 times together as well. All right, so plus 523 point, was it 81? Yeah. All right, there's my total time, 761.91. Okay, when should you round when you're doing physics? Right. Keep all of your decimal points until you're at the very end. When you have your final answer, round that. Don't round anything else. Okay? You can keep all those numbers in the memory of your calculator. If you don't have a TI-83 and it doesn't have a good memory function, then write down at least 3 or 4 decimal places. All right? That way you're going to maintain your accuracy. Because I see a lot of people when they're doing physics and they round off like the first number they have, and it makes a big difference if you use that number again. All right, so keep as many decimal places as you can. All right, so now I'm going to do this operation here to figure out my average velocity. 12,000, okay, divided by the answer I calculated there before, gives me 15.8 meters per second north. I probably didn't keep all my decimals when I did that because that should be 15.7 according to my rounding. But okay, everyone follow me on that one? Right, so if you have something with two parts, you got to find your total distance, your total time. Okay, keep going there, guys. Okay, guys, for number 7, when you get there, okay, this number here is 3 minutes, 29.46 seconds. All right, not 3 hours. You could crawl 1,500 meters in 3.5 hours. This is 3 minutes, 29.46 seconds.